Hess's law. Hess's law of constant heat summation, also known as Hess law, is a relationship in a physical chemistry named after German Hess, a Swiss-born Russian chemist and physician who published it in 1840. The law states that the total enthalpy change during the complete course of a chemical reaction is the same whether the reaction is made in one step or in several steps. Hess law is now understood as an expression of the principle of conservation of energy, also expressed in the first law of thermodynamics, and the fact that the enthalpy of a chemical process is independent of the path taken from the initial to the final state. Reaction enthalpy changes can be determined by calorimetry for many reactions. The values are usually stated for processes with the same initial and final temperatures and pressures, although the conditions can vary during the reaction. Hess law can be used to determine the overall energy required for a chemical reaction when it can be divided into two synthetic steps that are individually easier to characterize. This affords the completion of standard enthalpies of formation that may be used as a basis to design complete synthesis. Hess law states that the change of enthalpy in a chemical reaction is the same regardless of whether the reaction takes place in one step or several steps, provided the initial and final states of the reactions and products are the same. In other words, if a chemical change takes place by several different routes, the overall enthalpy change is the same regardless of the route by which the chemical change occurs. If this were not true, then one could violate the first law of thermodynamics. Hess law also allows the enthalpy change for a reaction to be calculated even when it can be measured directly. This is accomplished by performing basic algebraic operations based on the chemical equations of reactions using previously determined values for the enthalpies of formation. Combination of chemical equations leads to a neat or overall equation. If enthalpy change is known for each equation, the result will be the enthalpy change for the net equation. If the net enthalpy change is negative, the reaction is exothermic and is more likely to be spontaneous. Positive del S values correspond to endothermic reactions. Entropy also plays an important role in determining spontaneity, as some reactions with a positive enthalpy change are nevertheless spontaneous. Hess law states that enthalpy changes are additive, thus del S for a single reaction, where del SF is the enthalpy of formation of product P. Del SFR is the enthalpy of formation of reactant R, and the subscript indicates standard state values. This may be considered as the sum of two reactions. Examples: reaction A is the sum of reaction B and C, for which the total del S is equal minus 393.5 kJ per mole, which is equal to del S in A. Given other example, after multiplying the equations and their enthalpy changes, by appropriate factors and reversing the direction when necessary. The result is adding this equation and cancelling out the common terms of both sides. We obtain extension to free energy and entropy. The concepts of Hess law can be expanded to include changes in entropy and in Gibbs free energy, which are also state functions. The Borel thermodynamic cycle is an example of such an extension which takes advantage of easily measured equilibria and redox potentials to determine experimentally inaccessible Gibbs free energy values. Combining Del's values from the Borel thermodynamic cycles and Del's values found with Hess law can be helpful in determining entropy values which are not measured directly and therefore must be calculated through alternative paths. For the free energy, for entropy, the situation is a little different because entropy can be measured as an absolute value not related to those of the elements in their reference state. There is no need to use the entropy of formation. One simply uses the absolute entropies for products and reactants. Applications. Hess law is useful in the determination of enthalpies of the following: its of formation of unstable intermediates like carbon monoxide gas and nitrogen monoxide gas, heat changes in phase transition and allotropic transitions, lattice energies of ionic substances by constructing Born-Haber cycles if the electron affinity to form the anion is known, or electron affinities use a Born-Haber cycle with a theoretical lattice energy.